All right, cool. So today we have our third recitation, and we're going to go over some basic stuff for KKT conditions for optimization problems. And then I'm going to go over in pretty solid detail the Augmented Lagrangian QP solver that you'll have to write for homework 1. And then we'll have plenty of time for questions at the end. So let's go ahead and get into it. So the first thing is let's look at a canonical optimization problem. And so we're not saying anything about convex or non-convex. I'm just saying I have min over some primal variable x, some cost function f of x, then I have the following constraints. I have an equality constraint, so c of x equals 0. I'm going to have an inequality constraint, g of x less than or equal to 0. So the reason I'm going over this is because in class, Zach has now addressed the two specific situations. So he wrote down the KKT conditions for the case where we have just equality constraints. And then last lecture, or on Tuesday, he wrote about what to do when we have just inequality constraints. And now I'm just going to basically just point out the fact that when we have both these things, so we have both equality and inequality constraints, that all we do is just stack everything up. So here's I'm going to have a dual variable lambda that's going to correspond to this constraint. And then I'm going to have a mu, and mu is the dual variable for the inequality constraint. So now the first step with any optimization problem is I want to write down what my Lagrangian is. So we'll do L of x lambda mu equals, and here we have the cost function f of x. Then we have lambda transpose c of x plus mu transpose g of x. So here's our Lagrangian. And then now when we go to write out our KKT conditions, we're going to use this Lagrangian. So the first one is called stationarity. So stationarity just says that the gradient of the Lagrangian with respect to x must be equal to 0, which in this case is gradient of the cost function. And then I'm going to have the Jacobian of the equality constraints, transpose lambda, plus Jacobian of the inequality constraints, transpose mu equals 0. And again, I didn't say anything about this problem being convex or non-convex. These are just the first order necessary conditions for any optimization problem that takes this form right here. And so the first step was our condition for stationarity. The second thing is going to be primal feasibility. So primal feasibility. And what this just says is that the primal variables must be feasible, right? So what that means is that I just need c of x to be equal to 0, and then g of x should be less than or equal to 0. So that's primal feasibility. I'll just move this over. Now the next one is going to be dual feasibility. So dual feasibility. And now this one just means that our dual variables must be feasible, which won't dive into any sort of theory here, but I'll just say that mu must be greater than or equal to 0. And then this last one is our complementarity slackness or complementarity. So comp slackness, and I'm going to write this out a few different ways, and I'm going to explain that they're all in fact equivalent. So the first way is that, and this is how you'll see it written in like a lot of textbooks, is you'll see mu I times g I of x equals 0 for all I. This just means that the element-wise multiplication between these things must be equal to 0. So here's kind of like the first way you'll see this. Second way you'll see this is you'll see just mu and then some dot and then g equals 0. So this is the Hadamard product, which is going to be specific to what sort of inequality constraint you have. But we just have a normal inequality, so we're not doing anything with cones yet. So this is just element-wise multiplication. So again, this is the same as this. I'm just saying that the element-wise product of these things, if one of them is 0, the other can't be 0, and vice versa. And then you'll see another way that this is written down, which I think is actually the least helpful of all of them. This is where I just have mu transpose g of x equals 0. So what you'll see, and it's actually a quick question on your quiz, is that if I tell you that I have these two variables and they exhibit complementarity slackness, so when one is 0, the other is not 0, and vice versa, when I take the dot product of these things, I get just a sum of zeros, so I get 0. So me saying that the dot product of these things is true if these things are true. Now, the reason I don't think that this is that useful of a thing to write down is because this just means that these are orthogonal, which doesn't mean they exhibit complementary slackness. But these two directly say that, when one's 0, the other can't be 0, and vice versa. So I would say, I like this one the best, number 2. But in books and stuff, you'll see all 3 of these. Okay, so here are our KKT conditions. Now let's talk a little bit about what it means for a problem to be convex. So if the problem is convex, the cost function is convex, and the constraints define convex sets. And so if that's true for this problem that I just wrote down, then this KKT conditions are right here, or the first order necessary conditions. If I ever find a set of primal and dual variables, so x, lambda, and mu, if I ever find these 3 variables such that all these KKT conditions are true, then I have found the global optimal value for this problem. And this is kind of the magic thing about convex problems, is that there's only one local minima, and it's the global minima. So if I ever find anything that satisfies these KKT conditions, it is the best solution that I can get in terms of cost. Now, this is not true with non-convex problems. Non-convex problems can have many local minima that are not the same, and you have no way to find that you're in the global minima. But for convex problems, which we'll do a lot of in this class, these are sufficient for us finding the global optimum. Okay, so now I'm going to talk a little bit about QPs and quadratic programs. And this is something that Zach's mentioned a little bit, but it's going to be a super important part of this class, and we're going to use it all over because it's basically like the most mature of the convex problems that we can solve. It's very robust, and we can fit all sorts of crazy problems into this form. So now we're going to talk about QPs. And the reason this is important is because in your homework, you're going to write a QP solver that uses the Augmented Lagrangian method. So first, I'm going to go through and I'm going to walk through what a QP is, the KKT conditions for this, and then we'll talk about how to actually write an Augmented Lagrangian solver to solve this problem. So now I'm going to have min x 1/2 x transpose qx plus little q transpose x such that ax equals b, gx less than or equal to h. So in this form, if I ever have a problem where I have a quadratic cost function, so I can fit it in here, and again, I could have constant terms in here. I could have some constant that does not rely on x, but again, if I have a random value of my cost function that's a scalar and it does not depend on x, I can just forget about it and it doesn't change anything. It's not going to change the minimizing argument. Anything in the cost function that does not relate on x, we do not need. So I'll just say, we don't have to write down stuff like that. Okay. It does not change solution. So if you're ever doing stuff where you're reworking a cost function, which is something we're about to do, and there are terms in there that do not depend on the primal variable, you can forget those terms. Now, the reason this is nice is because if I have any sort of quadratic cost function, it'll fit in this form. If I have any sort of linear equality constraints, it'll fit in this form. And any linear inequality constraints, it'll fit in this form. So I'll give one quick example of a common control constraint that you'd find that you'd have to do a little bit of reworking to fit into this form. And you'll end up doing a bunch of stuff in this class. So this is like a super important skill to have. So imagine, I'll do a quick little aside over here. Imagine if I had the following constraint. Imagine if I said x must be between two numbers. So I have x is some vector. So say x is like my control input. X must be between the maximum value that x can take and the minimum value x can take. Now this is a linear inequality constraint, but it does not natively fit into this form. So the way I can write this is the following way. I'll rewrite it into two inequalities. I'll say x less than or equal to x bar, And then the second inequality, I'll say that, negative x less than or equal to negative x lower bar. So all I've done is I've taken this first inequality, I just wrote it out totally normal. And I took the second inequality, and I just threw a negative sign on there, and I switched the sign of the inequality, or the sense of the inequality. So now I have this right here. And then what I can do is I can just say, okay, I can rewrite this as the following. I can rewrite this as x. So this first equation is I times x. It's going to be less than or equal to x upper. And then negative I times x is less than or equal to negative x lower. And so what we did is that we started out with the constraint here that this is also called a bound constraint. So x must be between two values. And I wrote this thing out as two individual inequalities. And then from these inequalities, I just kind of showed you how using the identity matrix, I can write this thing into a linear inequality form that fits in this gx is less than or equal to h. So this would be, g h. So we'll do stuff like this in this class where we'll be given inequalities, and having the ability to kind of maneuver them around and understand how to put them into this gx less than or equal to h form is super important, because all QP solvers, they're going to use some form that's similar to this. They don't all use this, but you're going to have to be able to move constraints into a form that's going to fit into their description of what a QP is. So now that we're done with that little aside right there, we'll now go back to this problem right here. And as always, first thing we do is our Lagrangian. So Lagrangian, and again, I'll say that, we have a dual variable lambda for the equality constraint, a dual variable mu for the inequality constraint. So now I have my Lagrangian here, which is just 1/2 x transpose qx plus q transpose x plus lambda transpose ax minus b plus mu transpose gx minus h. So you may wonder, these were the constraints I was given. How come I took these constraints and I just threw, opposed to having ax equals b or b minus ax, I just threw ax minus b into this thing right here. And the reason why is because if you look at our original problem, what we said is that we want these things to be inequalities with 0 on the right-hand side. So for the equality case, it should be c of x equals 0. For the inequality case, I want g of x less than or equal to 0. So in order to fit in this form, I can't just say ax equals b. I have to say ax minus b equals 0. And hopefully that doesn't take too much of a leap to understand. So we took ax equals b. We just moved this over to the right-hand side. So I shall go ahead and I'll make this change over here. Minus 0, 0. Oops. I'll just move these dual variables over a little bit. Okay. So now I've written down these constraints in the form that we saw in the original canonical problem that we wrote down. And now we just wrote out the Lagrangian for our system. So now let's work through our KKT conditions. So the first thing we're saying is that we need gradient of the Lagrangian with respect to x should be equal to 0. And this is going to be qx plus q plus a transpose lambda plus g transpose mu equals 0. Now, the second set of conditions was primal feasibility. This just means that the primal variable x must satisfy the constraints. This is straightforward. This is me just saying, okay, ax minus b must be equal to 0, and gx minus h must be less than or equal to 0. And the next KKT conditions that we talked about were dual feasibility. And this is super simple. This is just mu greater than or equal to 0. And the last one is this complementarity slackness. And this tells us that mu element-wise multiplication gx minus h equals 0. So for convex QPs, and this is important, I didn't mention. For this problem to be convex, this right here, Q must be symmetric positive definite. So what that means is that it can have, so again, in a quadratic form, you can go and work this on your own, but basically in a quadratic form, this Q is always going to be symmetric. In fact, any non-symmetric parts of this are going to get nulled out by the quadratic form. This is like, if we have time at the end, I can go through this and show this to you. It's super simple, but basically, this term will always be symmetric, whether the problem is convex or not. But what we're saying, for it to be convex, it needs to be positive semi-definite. And what this means is that it can have 0 eigenvalues, but it can't have any negative eigenvalues. So if this Q had entirely 0 eigenvalues and it was just, empty, then this would be a linear program, right? So just Q transpose X, and linear programs are convex. Now, quadratic programs are also convex, but only if this Q is symmetric, positive, semi-definite. So, and when you see plus plus, this is positive definite. When you see 1 plus, this is semi-definite. This is eig vals, or I'll say min. Not the issue with this. This just means that eigenvalues of Q must be greater than or equal to 0. And you'll see this written as this positive semi-definite PSD. So that's how we know this problem is convex. So QP is convex if the quadratic term Q in the cost function is positive semi-definite. Okay, back to this. So now we have our KKT conditions. And again, this is a convex problem. So we know that any local minima is a global minima. And this tells us that if we find any set of primal and dual variables that satisfy these KKT conditions, that means I have the global solution to the problem. So for QPs, we're looking for this. So there's many different ways to solve this. Zach went over a bunch of popular ways in class, like active set methods, interior point methods. What we're going to do is we're going to implement, like, arguably the simplest way to solve these problems that actually works pretty well for a range of control applications. So what we'll do in the homework is we'll do the augmented Lagrangian. So QPAL solver. So what our augmented Lagrangian does is going to take the inequality constraints and the equality constraints, and it's going to put them into the cost function. It's going to minimize over an unconstrained problem, and it's going to update these dual variables. So I'm going to kind of go and walk through the sort of stuff that we're looking for when we set this problem up. So we have L in rho. So before, when I wrote down the Lagrangian, I said L was a function of X, lambda, mu. Now I have L with like a little row right here. And this tells me that this isn't my normal Lagrangian, this is my augmented Lagrangian. So this is augmented Lagrangian. So L rho of X, lambda, mu, rho equals, it's going to be our normal Lagrangian plus, and now we're going to add 2 penalty terms to violations in the constraints. So if I violate the equality constraints, that means that C of X is not equal to 0. That tells us that we have 1/2 rho AX minus B transpose AX minus B. So if we think about this, if AX equals B, so our primal feasibility is satisfied, our primal variable X satisfies AX equals B, then AX equals B is 0. And 0 transpose 0 is 0. So what we have here is that if this constraint is satisfied, this term is nothing. But if the constraint is not satisfied, it's going to have some penalty in the cost function. And then we'll do another term for the inequality constraint, and this one will be just a little bit different. So now I'm going to say that G of X minus H transpose I rho G of X minus H. So what I've done here is I've actually written down the same sort of constraint where I have some sort of quadratic in my inequality constraint. So, here's equality constraint, inequality constraint. Now, this I rho is going to be my selection matrix or my mask matrix. This goes by a few different names. And what it's going to do is it's going to have some logic in there that's going to determine if that constraint is active. So for inequality constraints, they're either active or they're inactive. What that means is that if it's active, so I'll write a little quick example about this. So an active constraint. So imagine if I had an inequality that said X, must be greater than or equal to 0. This is my inequality constraint. If my unconstrained solution satisfies X is greater than or equal to 0, then my constraint is not active. But if I have to add this constraint and then x star equals 0, then the constraint is active. So you imagine, if you think about this like graphically, if I had some thing here that said, the constraint must be, this side of the border, says, and here is the feasible set. Say my optimal solution is like somewhere over here, the constraint is not active. But if the optimal solution is on this constraint front, then the constraint is active. So what augmented Lagrangian methods do is they're trying to figure out which of these constraints are currently on this border and which of them are not on the border. So if you imagine, I'll write these out, this would be, so active, and then these ones, inactive. So for an inactive constraint, it's as if the constraint isn't there. We ignore it, right? It has no effect on this problem. And we can just say if the constraint is inactive, we'll treat it as if it's not there. If the constraint's active, then we kind of treat it like an equality constraint. So if x ends up being on this line right here, then I can treat this as if the constraint is x must be on the line. So this idea of active and inactive constraints is like a little weird, but I think throughout the class, when you play more with this, you'll kind of understand like how this really shows up in these solvers and why this is important, because there are inactive constraints that if they're not going to be active and they're not going to enforce anything, and they're naturally going to satisfy these constraints, then it's as if we don't need them at all, right? So most solvers will kind of like omit these constraints if they feel they're going to be inactive. Then there's active constraints like these ones, and in augmented Lagrangian methods, we're assuming that these active constraints are just effectively going to be equality constraints. They're going to keep it on this thing. Now, this is a huge difference from primal dual interior point methods, or just in general any like interior point method, because those treat every inequality constraint with the same like barrier function. And what augmented Lagrangian problems are saying is, don't treat all inequality constraints as like this barrier. Let's just deal with them case by case. So if it's inactive, ignore it. If it's active, treat it like an equality constraint. So all that to say that here's our augmented Lagrangian, and we're going to have a term here for violations in our equality constraint, a term here for violations in our inequality constraint. So now I'll talk about how we make I rho. So I rho is a symmetric matrix, so S, and it's going to be the same dimension as the inequalities. So number of inequality. And if you come from Python and you like doing things in a vectorized way, I'm almost going to guarantee you that when you create this matrix, so try and do something clever, I am going to urge you to do something that's just very simple and less efficient, but we'll guarantee you get the right answer. So what we'll do is we'll loop through. We'll do where I equals 1, 2, number of inequality constraints. And then I'm going to do the following. I'm going to say if g of x minus h, if this ith component is less than 0, so this is important. This is not a less than or equal to, this is less than, which means the constraint is inactive. And the dual variable for that constraint is 0, then I'll do the following. I'll say that I rho, I use Julia notation, I equals 0. So what this tells us, if the constraint is inactive, so it's as if it's not there, and the dual variable is 0, which it should be, then I can just forget about the constraint. Then I'm going to have this in my selection matrix, which is a diagonal matrix. I'm going to have that entry just be 0. So it's as if the constraint is not there. And then I'll say, if this is not the case, then the constraint must be active. And then I'll do I rho, I equals rho. So this is a foolproof, yet slightly inefficient way to create this matrix. But basically, you're going to create I rho to be zeros. And then just create this with the size of, these are number of inequalities. And I'm going to loop through each diagonal entry, determine if that constraint is active. If the constraint is active, then I'm going to have the penalty there. But if the constraint is not active and my dual variable is 0, which it should be, then I can forget about it. Then it's as if the constraint is not there. So I set that corresponding entry to 0. So this is our augmented Lagrangian right here. Here's the equality constraint term. Here's the inequality constraint term. And the equality constraint term is going to apply to all the equality constraints. It's going to put a quadratic penalty that's weighted by some value rho on all of the equality constraints. Then for the inequality constraints, what we did is we talked about those active and inactive constraints. And so this logic is baked into this matrix I rho. And here's how we create I rho. And what we'll do is we'll go through and at each diagonal, we'll determine is that constraint active or inactive. If it's inactive, we forget about it. If it's active, we treat it like an equality constraint and we just put a rho there. So if you imagine if all of my inequality constraints were active, this I rho would be a diagonal matrix with rho everywhere. And this would be mathematically equivalent for the equality and inequality cases. Okay, so now I can talk about, let's see. So I'll give you, I probably won't go through this because we don't have time, but I'll give you like a good exercise to do if you want to get like a better understanding of how to manipulate these matrix equations. So if I were you, I would like strongly recommend you do this. So I would take our augmented Lagrangian and for you, I'd rewrite it in the quadratic form. So I'd rewrite it, I'd move all the terms around, so I get this. And again, like I said last time in the previous recitation, we love quadratic forms because they're simple and they're easy to take the derivatives of. So what you should do is you should treat I rho as constant. Then do this. So what I'll do is when I upload the slides for this, I'll go through and I'll actually write all this out so you can see how it works. But I'm probably just going to bore you to tears if I do it right now. But it is an important skill, and you should be able to do it at some point. And so for the homework, when we write the augmented Lagrangian method, you'll need to know what these derivatives are. And you can use forward diff, but I think that it's like a little dangerous to rely on forward diff for everything. So if you're able to actually write this thing out by hand, I think it's super important. So now we'll talk about, I'll leave the rest of this page so I can, I'll add this. So TBD. After the recitation, I'll go through and I'll write everything out as to how we do it. And then you can check back when I post it on Piazza and you can take a look at how I did it. Or you can do it yourself, which would be cool. So now, QPAL alg. So now I'm going to write out the pseudocode for how the QP augmented Lagrangian solver is going to work. I'm going to specify everything. So if there's something in here, like there should be no reading between the lines. I'm going to specify everything. And if you have a question or you see me write something down that you're not familiar with or you don't know how you do it, like please speak up because like everything should be written out right here. So the first thing we do is we'll initialize. X is going to be equal to all zeros. Lambda equal to all zeros. Mu equal to all zeros. And then we'll start our penalty at just 1. Normally, this is like a big, normally like one of like the classic like tricks, I guess, to like weird optimization is normally choosing this initial penalty can have like a dramatic change on how the solver converges. We're not going to worry about that for this homework. We'll just initialize the penalty as 1, and this should work just fine for our problem. So this is our initial penalty of 1. And then we'll have some phi, and this is like a penalty schedule. This is 10. This tells me that as I increase this penalty on the constraint violation, rho, I'm going to increase it at the form rho equals phi times rho. So I'm going to up it by 10. So it starts at 1, then 10, then 100, then 1,000. It's going to go up by 10 every time I solve the augmented Lagrangian problem. And so here's how this looks. So for I equals 1 max AL. And so I'm going to write out 2 different ways you can do this. You can feel free to use whichever one you want to on the homework. They're both equivalent and they'll both work just fine. The first one is this first step is I'm going to solve the following problem. X star equals min over X So I'm going to solve an unconstrained problem for the augmented Lagrangian. And like I said, the augmented Lagrangian ends up being this nice, it's a nice quadratic form. So we use Newton's method on that. So the first thing we'll do is going to be an unconstrained optimization problem where I want to minimize with respect to x, the augmented Lagrangian. I'm going to make a note here that these variables, the dual and penalty, we're going to hold these constant. So I'm going to hold these three variables constant. I'm going to minimize over x, and this will give me x star. I'll just call this x again. So I'm going to update x to be the minimizer of this thing right here. And the next thing we'll do is update the dual variables. And then I'll make a note. This is use Newton's method. And this is actually an important note. You will not need a line search. So in this specific instance where we're solving QPs and the ones that we've set up in the homework, you can use Newton's method with alpha equals 1. So don't worry about thinking up like a merit function or anything. If you wanted to, you could use the augmented Lagrangian itself as a merit function. That's totally fine. But you should not need a line search for this problem. So use Newton's method. Alpha equals 1 is okay. Okay. And then the second thing we do is we're going to update the dual variables. We're going to update the duals, and we're going to do so in the following way. Lambda equals lambda plus rho times ax minus b. And then mu equals max 0 mu plus rho gx minus h. So if you remember, one of our KKT conditions is dual feasibility. And what dual feasibility says is that this mu, so the dual variable that is associated with the inequality constraints, this dual variable mu must always be positive. So when we do our dual update, we're just going to clamp it. So like whatever it is, it must be positive. And then the third thing we do is we'll update penalty. Update rho. So Zach in class kind of talked about how like technically you don't need to update rho. In our implementation and in almost every implementation, rho is going to get updated at some schedule. And so what we'll say is that we'll just do rho equals rho times phi. And we said before, we're going to initialize rho at 1 and phi will be 10. So every iteration, we're going to solve this unconstrained augmented Lagrangian problem, solve for x, which is the minimizing argument of this right here, using Newton's method. Then we're going to update the dual variables. And then we're going to take our penalty and we'll just multiply it by 10. And what we'll do is we'll say that we are converged when our equality constraints and inequality constraints are satisfied to some tolerance. So let me write out what that looks like. For check convergence. So what we'll do is we'll do, I'll do the infinity norm of ax minus b. So if you go, this is just norm, and then the value is the first argument, and then inf as a second argument. And also, you don't have to use infinity norm. You can use L1, you can use L2, use whatever you want to. It's most common to use the infinity norm for checking for convergence criteria. And what this will do is this basically tells you the max absolute value of everything in that vector. So what we'll do is we'll take our current equality constraint. And again, if we're converged, x equals b, right? So the infinity norm of this residual error right here is very, very small. So we'll check this, and we'll also check the following. So I'll say that g equals current inequality constraint, gx minus h. If g has to be negative, that means I'll check the following. I'll check g is negative minus, I think about this. So g is going to be less than 0. Negative g has to be positive. me think about this for a sec. I'm pretty sure this is right. So if G has to be negative, then negative G is going to be positive, ideally. And this should be like the entirety of this thing should be negative. And it should be quite small. So I will update this for the final slide, but I'm pretty sure this is right. But basically what we want to do is that like I want to make sure that everything G is very, very close to 0 if it has to be 0. If it's gonna be like inactive constraint, then like I'm not that worried about it. But I will certainly update this in the slide with the correct thing we want to use. Okay, so here's the augmented Lagrangian method.
Hey, Kevin.
Yeah.
We said that we are not considering any constraints in this case. Then why are we concerned about the conversions then? Like why are we updating lambda and mu? Because they relate to constraints, right?
So we have constraints, right? We have our equality and inequality constraints. What I said was that in this step 1, when I solve the unconstrained problem of just the augmented Lagrangian, I'm going to hold these constant, but I still have equality and inequality constraints, right? Does that answer your question?
Okay, that was just for the step 1 that you mentioned.
Yeah, exactly. Yeah. So
okay. I thought you were considering the whole example. Okay.
No, sorry. Yeah. So what I just wrote out, this pseudocode, this is true for a constrained QP augmented Lagrangian solver. So it's going to solve us for the solution of this problem. So we're solving this problem. Yeah. And so for convergence, we could do this thing I have right here, or we can just check the KKT conditions. So, or check KKT. Okay, and you can do whatever you want to for this. So, yeah, the question you asked is a good one. So we are ignoring the constraints just for this right here. So in step 1, we want to do is we want to find the unconstrained solution to the augmented Lagrangian if I hold everything else constant and just minimize over x. And what I said before is that we should write this thing out in a clean way such that we can take nice derivatives of this. And we'll just use Newton's method. And I said that alpha equals 1 is totally okay. So don't worry about a line search for this. But if you wanted to use a line search, your merit function would be the augmented Lagrangian itself. So anyways, I'm doing Newton's method. So I'm ignoring the constraints temporarily, and I'm minimizing the augmented Lagrangian. Then I update the duals. Then I update the penalty. Then I check convergence. And I'm going to keep doing this in every single one of these main iterations. I'm increasing this penalty, and I'm updating these variables. And so at a certain amount of time, I will converge. And we'll check this convergence either with the 2 things I wrote out right here, or we can just check the KKT conditions. They're both going to work just fine.